Good morning, good afternoon, good evening, wherever you might be, and welcome to another Science Post. This one's going to be quite physicsy, and it's mostly appropriate for people who are stuck in the thick of the undergraduate labyrinth of physics. It's called Maxwell's Equations in Wonderland. The conflict between intuition and mathematical rigor is best expressed through the relationship between the British physics of Maxwell, Kelvin, and Heaviside, and the French physics of Poincaré, Laplace, and Fourier. The French mathematical physicists looked down their rigorous noses at the analogies of British physics, all while intensely studying the British ideas and trying to translate the broad strokes into the narrow confines of their strict formality. Without access to the broader perspective, they derived mathematical results without fully understanding their application. With the certainty of a mathematician who wishes to supervise the physicists, Poincaré wrote, "The first time a French reader opens the book of Maxwell, a feeling of discomfort and even often of suspicion is mixed with his admiration. It is only with a long duration of commerce and at the expense of many efforts that this feeling dissipates. Why do the ideas of the English scientists have so much difficulty to be acclimated by us? It is probably because the education received by the French prepares them to appreciate precision and logic before any other quality." So, opening Maxwell, a Frenchman expects to find a theoretical whole as logical and as precise as the physical optics founded upon the ether. This way, he's preparing a deception. I'd save the reader in showing him what he must look for in Maxwell, which he cannot find. Maxwell doesn't give any mechanical explanation for magnetism and gravity. It is enough for him to show that such an explanation is possible. This was from Science and Hypothesis, Chapter 12, entitled Optics and Electricity. It was only later in Poincaré's life, after seeing the experimental work of the Curies, that he began to understand that those who do not think solely in mathematical frameworks can see things that he could not. True physicists like Curie look neither inside themselves nor to the surface of things. They can see under things. Mathematics are a trouble or even a danger when, by the precision of their language, they lead us to affirm more than we really know. This was Poincaré quoted in The Universe of Maxwell. In this post, I'm going to take a close look at what we really know about Maxwell's equations. I am going to try to use my imagination and look underneath them. In an earlier post, I wrote about magnetic monopoles and the existence of two sets of Maxwell's equations, Galilean and Lorentzian. Since this is not a familiar topic to most physics students, I'll spend some time unpacking the details. But since details are tedious to most people, I'll try to keep this light and whimsical. If you've ever read Through the Looking Glass by Lewis Carroll, you might remember the quote, "Jam tomorrow, jam yesterday, but never ever jam today." This statement about vectors and scalars always comes to mind whenever I see an equation expressing the expectation value for shear stress. Shear stress is not how you feel in rush hour traffic. It is the tension between two surfaces that are slipping against one another, and this is an important parameter because the amount of shear stress in a material tells you how it will behave when something interacts with it. If you have a lot of shear stress and someone hits you with a hammer, you might shatter into a million pieces. If you have a lot of sheer stress and someone hugs you, you might melt into a little puddle as the stress leaves your body. In this context, a particle usually acts like a hammer, and a wave usually acts like a warm hug. Of course, it is possible to deliver a violent hug, which can be as damaging as a hammer, as when a soprano hits a high note and shatters glass. It is also possible to gently caress someone with a hammer. This may be the reason that so many people get confused about what is a particle and what is a wave. They often act in similar ways, even though they are, from a philosophical standpoint, very different things. The reason that everyone believes that light is both a particle and a wave is because of Einstein's photoelectric interpretation. This interpretation also seems to follow from the fact that both electrons and photons can be used to do the double-slit interference experiment. But philosophically, this is a very literal interpretation, and both experiments could also be explained by quantized properties that only reside in the electron and not in light itself. If the detector of a light wave is always a particle, it shouldn't surprise anyone that the light wave sometimes acts like a particle. Likewise, if the particle rides on light waves, it shouldn't surprise anyone that the particle sometimes acts like a light wave. If this is too confusing for you to imagine, for example, in the double slit experiment, please picture a vortex with a wake behind it. As the vortex approaches the slits, it will slow down when it hits the barrier, and that will allow the wake to travel in front of the vortex, such that the vortex will ride on its own wake as it propagates through those slits, and that's how you get the probabilistic the quantum mechanical behavior from something that is quite classical. It's a story you should know, but you have to think about it a bit. What I'm trying to do here is to disconnect you from the quantum weirdness that is taught in many classrooms, and to reconnect you with a concrete picture of particles and waves that are fundamentally different things. In this picture, light and sound propagate through a sea of particles, moving those particles around like so many etheric grains of sand. This picture was nicely formalized by Dirac's sea of negative energy particles. But what is a negative energy particle? Is it nothing more than a particle that spins in the opposite direction from the particles surrounding it? I think so. The grains of sand that spin in a clockwise direction have a positive charge, and those that spin in a counterclockwise direction have a negative charge. The grains which vibrate in sync will attract one another, and those which are out of sync will repel one another. When you turn around and face the opposite direction, everything that you called a positive charge will now look like a negative charge, and vice versa. Physics couldn't be simpler. At least it was until the invention of Lorentzian Maxwell's equations, until Einstein popularized this concept. In the Lorentzian Maxwell's equations, light is Lorentz invariant. That means that it doesn't lose energy when it travels in a straight line. When light loses energy, one can either say that the wavelength got longer or the speed of light decreased. In the Lorentzian framework, instead of allowing a light wave to lose energy, the space in which the light wave exists expands, while the speed of the light wave is held constant. To some people of the time, this was merely a mathematical trick used to make the calculation easier. But to others, who have a really hard time separating figurative and literal concepts, they interpreted this as a literal stretching of space. In the Galilean Maxwell's equations, light is not Lorentz invariant. Space does not literally contract, and expand. Light can lose energy, and one keeps the wavelength constant while the speed of light changes when it, for example, enters a piece of glass in an optical system, or a gravitational field in a more cosmic system. But why did physicists abandon this set of equations with respect to large-scale planetary bodies while keeping this set of equations for other systems like optical systems? Why did they abandon this set of equations that made the physics of light in the cosmos and on Earth so wonderfully consistent and simple? The reason is that Galilean Maxwell's equations were hard to solve for some systems, whereas the Lorentzian Maxwell's equations made an approximation which removed a degree of freedom by eliminating the concept of the magnetic monopole, thereby making them easier to solve for some systems. But this came at a great cost to the etheric intuition and heuristics which had been developed over the previous centuries. In short, when Einstein popularized the Lorentzian framework and abandoned Cartesian space in favor of Minkowski's Riemannian mathematics, many people got very confused and forgot the utility of the Galilean Maxwell's equations. Some even forgot that they existed. Einstein had just learned of the Lorentz transformations, and when he saw the Michelson-Morley experiment, he concluded that over short distances, light does not lose energy when it propagates in a straight line. He inferred that this demonstrated the absence of ether and of the magnetic monopoles with which ether is composed. But, what a tragedy it would be if all physics students everywhere misunderstood such fundamental issues. We now know that other experiments, or many people know that other experiments, contradict this myopic yet still very popular inference. The Sagnac loop showed that light which travels in a circle will lose energy to the ether. Materials science showed that light which travels in tiny circles as it propagates, losing energy to the ether. Michelson-Morley experiments with electrons show electrons lose energy to the ether. But what is this ether? Today it might be referred to as a quantum spin foam, or a Dirac sea of negative energy particles, or a quantum vacuum. It would only rarely be referred to as a sea of magnetic monopoles. That would be a rather Fnordian way to do it. But whatever you call it, it appears to be a substance that conducts electricity. If it couldn't, an electromagnetic wave, or light, could not propagate through it. All school children are taught today that an electromagnetic wave is made up of electric waves which are perpendicular to co-propagating magnetic waves, and that the Lorentzian Maxwell's equations assure us that this is the truth. University students are taught that these waves are Lorentz invariant when they co-propagate in free space, but not Lorentz invariant when they do not co-propagate in a medium which refracts light, which is, okay. Very few university students wonder why this is the case, because they have a lot of sheer stress and a lot of homework to do. If they did wonder about this, they would ask themselves what sort of sheer stress could prevent the co-propagation of an electric and magnetic field in free space. Then they would remember that light bends in a gravitational or electric field when it has to swirl around something. In free space, that something would fit the definition or the description of a magnetic monopole. If light propagating through free space is really propagating through a sea of magnetic monopoles, like so many grains of sand, and that have and if this sea has a density or shear stress determined by the gravitational field, this cleanly and simply unifies the physics of the microscale and the macroscale. So, from this perspective, the Lorentzian Maxwell's equations are an approximation of a more complicated system that involves light propagating through a sea of sand of Dirac's negative energy particles, or a sea of magnetic monopoles. So now I'll break the process of light propagation down into its subcomponents. The electric part of the light couples to the charge swirling around the magnetic monopole, and the magnetic part of light is produced by the swirling charge around the magnetic monopole. The more magnetic monopoles a light wave interacts with, the more shear stress it encounters. When there is no shear stress, the coupling and the production have no delay and no loss. But when there is shear stress, there will be a small amount of energy lost to the sea of magnetic monopoles. On a larger length scale, the electric part of the wave couples to the electrons swirling around the nucleus, and the magnetic part is produced by the electrons swirling around the nucleus. On an even larger length scale, the electric part of the wave couples to the moons swirling around the planet, and the magnetic part is produced by the moons swirling around the planet. On an even larger length scale, the electric part of a wave couples to the planets swirling around the sun, and the magnetic part is produced by the planets swirling around the sun. On an even larger length scale, the electric part of the wave couples to the stars swirling around the galaxy, and the magnetic part is produced by the stars swirling around the galaxy. This recursive picture is just another way to describe a steady-state gravitomagnetic tired light electric plasma universe. There are some subtleties of interpretation regarding the difference between steady-state and tired light, and I addressed those in another post. These systems emit a light wave when the phase relationship between the light waves propagating between the center and the orbiting spheres produces constructive interference. Likewise, these systems can only absorb energy when the phase relationship drifts or shifts in the opposite direction. The amount of energy absorbed or emitted is quantized because each orbital has a defined amount of energy, and the orbitals only interact with one another when the plane of one wave discretely rotates, as when the spin or angular momentum of a particle flips upside down. I regret that I have let this get so complicated. I wanted to stay light and whimsical, but here we are, stuck in the details. To zoom back out again, the picture of Lorentzian Maxwell's equations, electromagnetic wave propagation in a vacuum, is wrong because it approximates space as being empty when it is really full of magnetic monopoles that are better described by the Galilean Maxwell's equations. The underlying reality is that a magnetic field only appears in the vicinity of particles, or as a wake behind a purely electric pulse. Since all of our light detectors use electrons in some way, and charge swirling around a particle always gives rise to a magnetic field, we have assumed that the magnetic field must always be present, even in free space. But this was a Lorentzian approximation of a Galilean Cartesian free space which is full of magnetic monopoles that have a density determined by the strength of the gravitational field. Awareness of this approximation requires the recognition that Lorentzian Maxwell's equations are only valid in the presence of matter, and the description of light propagation in free space is an approximation. The Galilean Maxwell's equations are required for an accurate description of the propagation of light in free space, because it is only when the energy of a wave is transformed into a swirling motion in the presence of a particle that the magnetic field is created in a sea of magnetic monopoles. To prove that light in free space is electric and not electromagnetic, you would need to have a purely electric wave, which gives rise to the appearance of an electromagnetic wave within a detector. And that is exactly what is observed in particle accelerators, the sorts of machines I worked with for 20 years. So wrapping up, I will say that to make the math of physics match up with sensible heuristics that are tied to all of our observational evidence, we need to recognize that light is an electric wave in free space and an electromagnetic wave near matter. An electromagnetic wave in free space is a Lorentzian approximation, and in the Galilean Maxwell's equations, free space is filled with magnetic monopoles that have a density determined by the gravitational field. The Michelson-Morley experiment could not distinguish between these frameworks because it was interpreted with the heuristic of electromagnetic waves while using a Lorentzian mathematical formalism that described electric waves. So they mixed and matched their heuristics and their mathematics, which is the same mistake that has been done with general relativity. So the transit time of the electric wave in one arm was actually changed, but the particles used to detect the wave had a slowed clock, which perfectly compensated for this path length change. This can be explained with special relativity in terms of length contraction of the particles in the mirrors. Returning to Lewis Carroll's "Jam tomorrow, jam yesterday, but never ever jam today." When people focus on a single moment without connecting it to a larger narrative, they sometimes forget that they are making an approximation of a more dynamic system, as in quantum mechanics. The Lorentzian Maxwell's equations are an approximation in which magnetic monopoles are defined to be non-existent. The quantum vacuum is defined to be non-existent. This is all well and good when you are working with systems in which the quantum vacuum can be approximated with a displacement current and virtual particles, but it removes the vital etheric intuition required to unify the physics of systems large and small. Thank you for listening to this. I hope that it supplements the narrative you got from your teacher, because all teachers have not heard the same stories, and these are the stories that I heard in my undergraduate education. And I want to pass them on to you so that you can combine them with what you know and pass them along as you see fit. Thank you very much.